Since its invention about 100 years ago, mass spectrometry has become an essential tool used by many scientific and medical researchers. Mass spectrometers are used to identify the type of atoms. Today, many different types of mass spectrometer are in use. In this activity, we shall study the working principles of the Bainbridge mass spectrometer. The mass spectrometer is used to determine the masses and relative abundance of the different isotopes of an element. The main components of the mass spectrometer are the ionizing chamber, accelerator, velocity selector, deflection chamber, and detector. Click the Label button. We will now look at the function of each component of the Bainbridge mass spectrometer. The sample is first vaporized by heating and then enters the ionization chamber S. Click the Ionizing Chamber button. The electrically heated metal coil emits electrons which are attracted to a positively charged plate called the electron trap. Collisions between the electrons and atoms of the vaporized sample produce positive ions. These positive ions are pushed out by the positively charged ion repeller. The positive ions are then accelerated, pass through 3 slits and emerge as a collimated beam. Click the Accelerator button. Ions with different velocities enter the velocity selector. Click the Velocity Selector button. In the velocity selector, all the positive ions experience an upward electric force and a downward magnetic force. For ions with a certain velocity, the two forces are equal in magnitude. These ions move undeflected through the velocity selector and emerge from the slit S2. When these ions enter the deflector, they experience a magnetic force that causes them to move in semicircular paths. The radius of the path of an ion depends on its mass and charge. Since all the ions have the same charge, lighter ions are deflected more than heavier ones. Click the Deflection Chamber button. The detector can be a piece of photographic plate. Ions with different masses strike the photographic plate at different points. Click the Detector button. The mass-to-charge ratio of an ion can be determined by noting the values of the electric field E, the magnetic fields B and B', and measuring the radius of the path of the ion. The ions that leave the velocity selector have the same velocity v. Click the Expression for v button. An ion of mass m and charge q in the magnetic field B' of the deflection chamber experiences a magnetic force which causes it to move in a circular path of radius r. Click the Expression for mass to charge button. Ions of two isotopes of uranium, uranium-235 and uranium-238, move with a speed of 1.15 times 10 to the power of 5 meters per second in the deflection chamber of a Bainbridge mass spectrometer. The ions are all singly ionized and the magnetic flux density is 0.750 Tesla. What is the distance d between the two marks on the photographic plate? Click each step to see the solution. Notice that the mass spectrometer is able to convert the small difference in mass into an easily measurable distance of separation. What happens to the radius of the path of each ion if the magnetic field is increased? Answer: with a stronger magnetic field, the radius of the path of each ion decreases. A strong magnetic force acts on the ion, causing a greater deflection. Summary: in the Bainbridge mass spectrometer, the mass-to-charge ratio of an ion is given by m/q equals b prime r over E.